In this second video, Mark Bohr describes what caused Dennard scaling to come to an end. From both technical and end market perspectives, Mark's third era of Moore's law was marked by rising power constraints that came at the end of the Dennard scaling era. Increasing frequency was driving power needs up, making continued simple scaling of just shrinking dimensions unviable. But recognizing the change was not that easy because entirely new ways of scaling devices were needed. Mark describes how this again drove changes in devices and processes and brought on one of the most innovative eras in semiconductor process history, where adding new materials and structures were needed to keep Moore's law alive. The industry had to pull many new cards off the periodic table of elements to make devices viable. By the way, 2 more videos follow this one, which include the scaling and heterogeneous integration era and Bohr's rules of innovation. But for now, let's hear what Mark has to say about the power-constrained era. On the one hand, you had this question of how do I get forced to liquid cooling, like what some of the competitors did, and so you saw these, PC competitors with chips sitting on in radiators and looking like a car engine.
Yeah. So there was a lot of talk and some research within Intel about liquid cooling techniques, but I think we engineers at least pretty quickly recognized that's not a very practical solution. Liquid cooling is an expensive additional feature on any desktop processor, and it's certainly not compatible with the mobile market that we are now starting to get into.
It wasn't where the market was going.
Not where the market was going, yes, exactly.
And that's an important thing, is to have the technology aligned to where the market's going.
You've got to be able to follow where the market wants to go, not just what your past vision was.
So that ended around, Dennard scaling ended around 130 nanometers, and right, and now we get the power constrained era, right? We hit the power constrained era, and that really changes everything, right?
Well, it does. We realize as engineers and as circuit designers that we have to move on a different path, develop technologies and develop chip designs that focus more on power efficiency and not just on a raw frequency increase. So we had to do something different on both sides.
And up to that point, right, it was largely just shrinking, making the existing materials more efficient. And all of a sudden we started looking at the periodic table and pulling cards off of it, right?
Well, again, it's interesting to look back at the Dennard scaling era, where a lot of people in the industry were very proud and dependent on the roadmap.
Mm-hmm.
We all knew that in 3 years we'll be here, and then there, and then there. Well, once we had to exit the Dennard scaling era and move into the more power-constrained era, we were facing the need for continual inventions and innovations, like high-K metal gate, strained silicon, etc., and others in the circuit design and architecture side. So it was both a series of inventions by the process technologists and a series of inventions by chip designers.
I remember when we got into that era too, there was a big brouhaha where people were saying nanotechnology was going to take over the industry, and the chip business was dead because the fabs were getting too expensive. And Sunlin Cho, who was the running TMG at the time, pointed out that at that 130 nanometer jump, we were already below 100 nanometers, which was the definition of nanotechnology. And we started to move from calling everything, by microns to nanometers, right?
That's right.
And but then when you look at under the hood, right, your first big invention was strained silicon, right?
Yeah, so at that 90 nanometer generation in 2003, we realized, hey, we couldn't keep scaling the traditional transistor structure that used silicon dioxide and then polysilicon, and without incurring much higher leakage levels, intolerable. So we came up with strained silicon, a way of staying with those known materials in the gate electrode, but still enabling a way to get improved transistor performance without incurring a higher leakage power. So that was the first of some important innovations needed in that power-constrained era.
But it wasn't enough, right?
And it was enough. That lasted for the 90 and the 65 nanometer generations. But then we were back up against another wall. Gate oxide leakage, still high with SiO2.
I remember you teaching me about only 5 atoms.
Well, it was only a handful of atoms, so yeah, there's not much scaling room there. And again, gate oxide leakage had become a very noticeable portion of total chip power. So that was not something that could be continued. So we then focused on getting high K metal gate ready, came up with the right materials, and introduced that invention on our 45 nanometer generation in 2007.
In both of these instances, there were a lot of people working on the same technology, but Intel in both cases was the first to do it in volume manufacturing, right? And that's the big distinction.
I think that's a very important point. It's one thing to research an idea and to maybe have some papers or lab results to say, hey, we got something promising, but it's a much bigger thing to take a technology and not only have it ready for manufacturing, but have both the management will and confidence to agree to what the engineers are telling them.
Yeah, so then, because the next big one is even a much bigger leap, FinFETs. And people said you could only do a logic transistor in FinFETs, right?
So the FinFET idea had been around for a while, again, as a good laboratory idea. In fact, I still remember when the first FinFET paper was published at IEDM, I think back in 1989, and I was in the audience, and I remember way back then thinking, what a crazy idea, this will never work. But by the time we were, it got to be 2010 or so, we realized, we'd done strained silicon, we'd done a high K metal gate, but we're still bumping up against some significant power efficiency walls. And the more we looked at FinFETs, or tri-gates as we called them at the time, the more we realized this is going to be a significant performance and power advantage. Now, it took some work to convince not only our circuit designers, but some of our managers that, hey, we could make this manufacturable, but we did.
And then that ran out of steam, and so then you had to go to what you call hyperscaling, right?
Well, FinFETs are a great technology and still working well for us today, but what we recognized several years ago is that process technologies were getting to be much more complex. Now, many more masking layers, much more stringent design rules, more materials, and it was simply taking us longer than 2 years to develop such a technology and have it ready for high volume manufacturing.
Mm-hmm.
Now, we could have just stayed on the normal scaling path, but go back to doing it every 3 years instead of every 2 years, but we didn't want to walk away from our goal of doubling transistor density or more. So we came up with the hyperscaling technique, where we get more area scaling, more density improvement at each step, even though it would take us longer to do that step. So it still keeps us on that density improvement trend, even though it's taking us longer to develop these more complicated technologies.
And some of the things that happened in that era went along this lines, right? Like we had single core, right?
Yes.
And we moved on from there to...
Well, again, you're raising a good point. This power-constrained era is not just an era of process innovations. There were some significant microprocessor design and architecture innovations. First of all, going from a single core to dual core to multi-core, and now heterogeneous cores, where you combine small lower power cores with the larger high performance cores, and other design techniques like power gating, where you turn off circuits that are not in use to save power, or turbo mode, where the processor operates at a moderate frequency for most of the time, but when you have a really performance critical application, you can boost the frequency just for long enough to get that job done.
We're going to pause the conversation right here. Please look for the upcoming continuation of it in the near future.